And now to close our day and get ready for the welcome reception, we come to one of the most popular sessions of the symposium, the lightning talks. Today you're going to hear about topics related to GeoAI from a few different perspectives. Your speakers range from graduate students to CEOs and everything in between. The one thing they have in common is they are passionate about their topics, and these presentations are often among the best you will see over these 2 days. So the first presentation is going to be Making a Case for the Human, Maggie Cawley.
This okay? All right, ready, go. I've got 10 seconds. Hi, everyone. My name is Maggie, and I am a human. It's great to be here. Thanks for having me. So for all of you deep thinkers out there, I think I have 13 seconds per slide. There we go. I just want to give you a warning. This is an exercise in oversimplification. These are not peer-reviewed slides, and I hope to kind of make everyone laugh after a nice long day of interesting discussion. So first, let's get our terms down. Humans. All right, we're distinguished from other apes by a large brain and the capacity for speech. That's really helpful, right? That's great. A person, a human being. Thank you, American Heritage Dictionary. Artificial intelligence. All right, capability to do algorithms and imitate intelligent human behavior. Intelligent human behavior. Great, okay. Now that we got our terms down, let's kind of see who's in the room. Who are our techno-utopia folks? Raise your hand. Who thinks that we're going towards existential dread with AI? Any existential dread? Anybody in the middle? All right, so why am I talking to AI? Well, I don't really have a lot of experience with it, but I think the two main things on this list are that I'm generally skeptical of hype, and I have a lot of guilt around excessive consumption, especially water. This is how I think AI works. Again, an oversimplification, but what you put in it, it simplifies for you and hands it to you. So here we go. A case for the humans. And I have to emphasize, this is not a case against AI, but rather the humans. This is a picture of humans at State of the Map US, very mappy humans, and I think happy. So the first thing I love about humans is their passion. It's very unique. Whether they're solving equations or marching in a band, they do it with gusto. I don't know about this thing on the right, but you can listen to it and see. Humans have a balanced-ish diet. We can eat insects, we can eat plants, we can eat animals, but the AI diet's pretty standard. They eat the same thing all the time. Humans use less water, to believe it or not. I don't know if they're both humans or one of them's a human up there or none, but down to the chip, a single chip uses thousands of gallons of water a day. And a lot of our water goes to things that we can actually consume later, which is really helpful. Whether we're growing food or we can't eat a selfie, though, as far as I know, or combining animals. Humans still map buildings better than ML. I had to push this one in here, but the youth mappers just took care of this for me. And where we've come a long way, we still see humans building more beautiful maps. LLMs are good for lots of text things, but for images and spatial reasoning, it's still not quite there, unfortunately. I think my next point is one of the most important ones. Come on. What would you rather have on your couch? Just leave that. So, many companies are racing towards this future that we don't really know what it looks like, but they're running. They're running there towards it, towards the money, towards this winning of AI, whatever that means. But I gotta say, there are a lot of the humans that brought us to where we are today going the other way. That's gotta give us pause. What are they running from? And as humans, we love movies. And I think a lot of truth happens in movies, and we can't say that our past human friends haven't tried to warn us of what we're really running towards. What are you gonna do? So can we not rush toward oversimplification of our lives, but rather value ourselves for empathy over efficiency? What happens when everything is a nail? What does 2050 look like? Do we measure each other in efficiency? Is it empathy gone? What do we want to build? And I'm happy to be here with all of you to talk about this. I'd like to invite you to my next talk, making a case against humans, because goodness knows, I mean, do we really want to give humans this technology? So thank you very much for having me. That's all I've got.
Thanks, Maggie. That was great. And next, Ms. Arianna Flores and Ms. Paige Hebert, GeoAI for a Thirsty Planet, forecasting harmful algae blooms.
Hi everyone, my name is Paige Hebert.
And I'm Arianna Flores, and today we'll be talking about how GeoAI is transformative for forecasting harmful algal blooms.
We're both students deeply interested in water issues and wanted to explore how water quality and water scarcity are impacting our lives now and in the future.
So we specifically examined Cape Town, South Africa, because in 2018, the city experienced a day zero water crisis in which an extreme drought almost forced the city to shut off water for all the residents. However, this isn't just a water scarcity problem, but also a water quality problem. When the water levels drop, harmful algal blooms become much more likely. With less water, nutrients become concentrated, which helps these toxic blooms grow. HABs lower oxygen, release toxins, and can make drinking water unsafe. As water becomes scarcer, the quality of our water becomes a major concern.
We decided to focus on this issue at the Theewaterskloof Dam because it's the largest dam in Cape Town that provides nearly half of the water supply for people in the city. So understanding it and managing it is crucial. This area has experienced large bloom events and was significantly influenced by the day zero water crisis. You can see how both water extent recedes and dark green indicators of possible HABs appear. This helps us understand how both of these factors are influencing water access.
Harmful algal blooms are becoming more prevalent and worsening as climate change progresses. Our entire planet will face water challenges and their consequences in the future, and we already are. Events like those in Cape Town will happen more often, so utilizing data to understand and solve these problems is crucial. Harmful algal blooms seriously affect people in desert regions like sub-Saharan Africa, but many cases aren't reported because of limited infrastructure and resources. A lot of HAB impacts simply never get logged, which is why maps like UNESCO's show almost no data for Africa, but tools like GIS and GeoAI can change that. They let us detect blooms with multispectral imagery and use predictive modeling to spot risks and help us prevent these risks.
So GeoAI can be an agent of change because it can see chlorophyll A, turbidity, and other bloom indicators through multispectral bands, illustrating what we don't always consider. It's transformative because GeoAI enables more thorough and detailed analysis. By taking satellite imagery of water over time, AI tools within the image analyst toolbox can process the multidimensional data and detect HABs more accurately. These specific band combinations and pattern analysis can detect blooms, but GeoAI can also predict future blooms. So we use Copernicus Open Access Data Hub for data with satellite imagery bands 4 and 5 for the Normalized Difference Vegetation Index. With satellite data tiles from 2016 to 2024 in Cape Town, we created a time series and then implemented classification with AI techniques using change detection tools. We created this map predicting trends of where HABs are likely in the future, the green areas indicating high-risk spots. As you can see, there's more concentration of bloom risk on the west side, and this makes sense because, as you could see from the maps before, most of the drought occurred on the west side of the dam as well. Obviously, the model can be improved. We, of course, were limited by time and knowledge, so predictions could be more accurate and precise by creating multiple custom band indexes that specifically highlight indicators beyond just the two we used. And in the future, you could also take it further by training a deep learning model. So this entails training samples for pixel classification and change detection within the area of interest. We didn't have the time or resources to train a deep model yet, but the data generated so far makes it clear the possibilities and applications are vast. This is just the beginning, and although we don't have everything figured out, what we do know is that initial experimentation with GeoAI techniques for HAB prediction in Cape Town shows immense inspiration and promise. It is actionable and impactful to gain a better understanding of our water in the future and the threats these sources face. It could expose the issue with data and allow for improved water management that minimizes the effects of these bloom outbreaks.
Now, looking ahead to 2050, these models can scale even further with deep learning and global GeoAI systems. They can help us predict water quality with much better accuracy and catch harmful algal blooms before they become dangerous. Most importantly, implementing these tools in places like rural Africa, where reporting is limited, could truly change lives. GeoAI provides a means to fill those data gaps and build a safer, more informed future for global water security. Ultimately, it's exciting to see how GeoAI enables us to shift from reacting to water problems to proactively addressing them. By forecasting toxic blooms, we can make smarter decisions about how reservoirs are operated, when to issue emergency warnings, and even how to protect global food security.
We're just starting to scratch the surface here, and the possibilities with GeoAI for HAB prediction are great.
And the impact could be even greater.
GeoAI gives us the opportunity to see these crises before they arrive and act before it's too late. So what it's really giving us is hope for a shared future.
Thank you.
And next we have Dr. Jeffrey Hamerlinck, who's going to talk about AI for smart rural places, bridging the smart divide.
That was super interesting. That was really great. So yeah, Jeff Hamerlinck, University of Wyoming, AI for smart rural places, bridging the smart divide. Oh, I didn't time the first slide, right? So my comments are related to the Smart Rural Places and Community Scale Digital Twin Demonstration Project that we're undertaking with the Center for Rural Resilience and Innovation at the University of Wyoming. I'd like to say 4 things about smart rural places: the smart village concept, the socio-technical components that make up a smart village, the role of digital twins in GeoAI, and then what are some of those implementation challenges, specifically with the AI smart divide. So if you look at this diagram and you start to think about what makes up a smart village, and it's everything from those ICT kind of components that are appropriate for rural, the governance that goes along with that, all the way down to services and the applications. But really at the end of the day, it's about maintaining a rural way of life, improving livability there, but integrating technology and innovation and addressing some of these solutions. It's also unique in that these aren't smart cities. They're very different. The types of problems being addressed, the way you engage with the community, the way you govern, infrastructure issues, et cetera. If we look at this sort of smart village conceptual framework, you see a lot of different boxes there. This is from a publication in 2020. You see things like the Internet of Things, sensor networks, a central database, data visualization tools, all leading into these services around education, democracy, governance, and people. Fast forward 5 years to today, the things in the green box are kind of still the same, but everything in that black box we could probably replace with this idea of a digital twin framework enabled by GeoAI. Oh, I really sped through that one, didn't I? Well, take it all in. It's a complex diagram. So coming back to the human pieces of this, we've talked about the digital divide for a long time, and in rural places, maybe we think of, is my broadband going to be there, right? But let's think a little bit about this idea of the smart divide. What more is happening there? And what we're really talking about there are the social inequalities that are tied into this imbalance in the penetration and matureness of this smart infrastructure and the applications and the services, but also on the human side, digital literacy and skill gaps across urban to rural, but also between different segments of demographic characteristics and socioeconomic situations. I'll get to look at the slide a little bit more. And so when we think about rural community AI adoption, or in the sense of doing local digital twins, GeoAI adoption, what are some of the barriers that we might face? So we talked about digital literacy a little bit. These are those kind of specific technical skills to use AI tools effectively, not only for citizens, but also for professionals working in those rural cities and counties and small villages. Lack of tailored tools. A lot of the R&D that's happened with AI has been urban focused, and so those models are not trained on rural data, and they might not be relevant in rural settings. And then finally, with weaker infrastructure, there are concerns in particular sectors, agricultural, healthcare, for example, around privacy and cyber infrastructure risks if those checks and balances aren't in place. More thinking. And so just to wrap up, what are some of the ways that we can try to address this, and what are we doing in our particular project? One of the things that we're particularly interested in exploring comes out of Finland, this idea of creating rural living labs, the idea of bringing stakeholders together really around this concept of knowledge co-production or knowledge co-design as a way to get people to the table, identify different perspectives, build research questions and solutions together in these kind of laboratories. Universities and land-grant universities in particular in the US are well suited for this. Understanding AI social acceptance. So we're looking at this at a broader scale in the Rocky Mountain West. What are people's values in terms of why they are where they are? What are their needs related to technology? What are their viewpoints about privacy? And how do we build trust around new innovative technologies? And then ultimately, what are the benefits, and is there a return on investment with that? One of the things that we're looking at is the critical theory of social acceleration, this kind of connection between technology acceleration, social change acceleration, and pace of life acceleration. The need to grow constantly maybe isn't always a good thing, right? And so we're trying to use theories like this to explore some of those questions and identify opportunities and barriers. Thank you.
Ms. Gwendolyn Murphy, who's going to talk about the role of STS in the age of deep and twin transition.
Hey y'all, I've got just 5 minutes to explore how science and technology studies and critical geography are going to help us ground truth twin transitions, revealing where our material realities are diverging from the promise of our GeoAI projects. So situating us in our priorities, we're here today as geographers to grapple with our role in the digital transition. At the same time, global leaders in Brazil are debating pathways to net zero through the energy transition. These transitions intersect through shared technologies, supply chains, governance pressures, and the use of AI to automate our decisions. So much so, it's often called the twin transition. So I'm going to focus on these material requirements. These technologies rely on more than 60 elements, and for copper alone, we're projected to mine more in 2 decades than all of human history prior. So we're talking about extraordinarily large quantities, diverse sets of needs, and short timelines in the next quarter century. So we need to know where and in what quantity our supplies are located. To do that, a geospatial data scientist, energy policymaker, and a geologist might walk into a bar and create an energy transition mineral data repository. So institutions across sectors, including our own lab, are calling for this. We have the tools, the capacity to produce something that is globally comprehensive, digitally accessible, and so it's tempting to believe that's enough. But geographers, we are natural designers. So from hand-drawn maps to digital platforms, there's a few basics we know. What data counts, how to interpret it, and what to visualize and emphasize. So zooming in on the data itself, we need to question what we're using and considering as supply or a deposit. So predictions of these soaring mineral demands, and to be clear, this is for renewable energy, so it could double, triple, or more, depending on AI or society's consumption patterns. But all of these data sets are shaped by national interests and geological constraints. So what can be mined from below ground? And this is important because there are significant gaps between what these mines can offer and our actual targeted needs in the next 25 years. So the solution is usually more mines at any means, often in highly vulnerable areas. Almost 70% of all mines are on or near indigenous or peasant lands, and there's severe sociological harm and violation of international consent laws. I actually came from COP30 last night, which is actively on fire at this moment for people who are not aware, which feels symbolic of the issues. But there are significant tensions between these material needs and extractivism-driven human rights violations. It also doesn't solve the issues, as mines typically take 15 to 20 years to come online. So our challenge is to design without being mired in logic of who or what must be sacrificed. So we need to challenge what data we're looking at. A deposit exists anywhere the material does. Our supply exists both in rocks and in materials circulating through time and space. So an airplane alone contains 17 of these elements, and this knowledge allows us to see that supply is everywhere. It's in airplanes, ships, tailings, and landfills, and mapping above-ground resources is going to strengthen our supply security and kickstart the circular economy, which is necessary by the IEA to meet our transition goals. It also allows us to integrate existing transit systems into supply decision support to plan better for a growing future supply as these materials are moving. So these expanded deposit definitions are going to help guide strategic extraction so we can we can meet our demand more responsibly and in line with our development goals. So we need to take maps and expand them to include other factors like pollution, biodiversity, and ESG risk as well. This will allow us to choose supply that reduces harm rather than justifying it when our decisions are made out of context. To put this into practice, we need to question what our core problems are when our GeoAI projects. So if our goal is actually to reduce emissions in these projects, then we're going to need to weight our tools to select deposits to minimize distance between supply, manufacturing, and demand. This is crucial because the transportation sector alone is on track to push global warming to 4 degrees Celsius, far above the 1.5 to 2 degree targets discussed at COP. So we have real impact in reshaping global manufacturing chains with our designs to bring us closer to sustainable futures. The design of our data system truly matters. It determines what possible futures our decision makers as well as our AI tools can see. So rather than deepening historical harm of people in place, let's boldly redesign and let go of processes or systems that don't serve us. Stupid rapid fire last thoughts I'd like to leave you with, and that is how data affects sovereignty and autonomy, making sure we question our methods of collection and curation, how its commodification of data extracts value from vulnerable communities, and any unintended consequences of use. So in summary, the industry and academia often assumes the twin transition automatically delivers energy security. But for whom and at what cost? We need to instead apply deep principles to restructure our systems to center efficiency, protection of vulnerable people and ecosystems, equitable resource governance, and transparent, accountable data and supply flows to align the twin transition with energy sovereignty as well. A parting question, is it really STS or just good design? Thank you.
Dr. Hamid Norouzi, who's going to talk about a predictive heat model for New York City subway system.
The system does not have a reliable, basically, understanding of how bad the situation is to have engineering solutions for them. And that's something that we started this collaboration with again, we reached out to MTA, and MTA said, okay, thanks for your service, for collecting that data for us. You could start from these stations. And what happened is that we started collecting data from 112 stations. We collected infrared imageries and as well as the air temperature and humidity, and 60 students were involved. And this was over 2 years. And that's something that pretty much every weekday, we didn't collect weekends, but weekdays that we collected data, and it's something that a very comprehensive data of what we had from 4 boroughs. We haven't forgotten the Staten Island, and we'll get to them, but it's something that we reached out and we tried to specifically pick stations with particular cooling system. And what happened, the 10,000 data points lead to some analysis that we could do for each service lines, the number of passengers that are using them, and how effective these are color-coded differently by the cooling system that are implemented. And for instance, we found that Bronx has the lowest temperature, but the humidity actually makes it much worse for the service line in that area. And it's something that they have to consider if the riders is something that they are focusing. So maps, we try to map our data collections, and it's something that we found that, okay, the heat index is something that the riders probably more can relate and can care about, and it's something that showed the distribution of what's going on. Some terminal stations had worse situation, and it wasn't really equitable in terms of how bad things are across the city. And so what we did, we compared on the very right of you, the map on the right is just something that the differences between the street level and the platform level was mapped to see that if we can quantify it as the stations. We noted that the terminal stations are the ones that the cars actually do a lot of idling, the trains, and that generates a lot of heat, and that makes them actually worse. So it's something that should be actually taken into account. So we came up with the idea of can we have a forecasting model, like a weather forecast, like a forecasting model for the platform level for the next 10 days. If we have the outside temperature forecast, and it could be actually generate platform temperature, and that's something that we brought our AI model actually was able to do R-square of 91. We're really happy about the results, and we are trying to extend them into understand the impacts of the platform structure, the architect, and the facilities in those. And the results were, eventually we started a website, subwayheat.org. It's just to start putting out the data, and it's something that we are trying to add the forecasting to be added to the system, so it helps the policymakers and hopefully the writers to understand. We collected a lot of infrared images. This is an example that I want to show. Up to 116 degrees Fahrenheit basically were kind of detected. And it was just something normal. It's not something that I'm picking one extreme for you. We had a lot of examples of this. And it's something that we try to see that the issue of the fans that I mentioned would makes it worse, 116 to bring it to the 90 level. So it's basically making that mixing happen. So we thought that, okay, can we take these 7,000 images so far, which is growing, to see that, learn basically how the heat is being actually transferred to underground. And we found that the columns, steel columns, are the ones that they are conductive and they send the heat down. The cars, the facilities, the equipments are there. So we came up with the image processing, a workflow, and an AI model to try to automatically basically segment different parts or equipment at each station over time, over different stations, to better understand the system.
Thank you. So I'm here to speak about Quantum Almanac, where we explore how AI and quantum computing can be leveraged to create targeted high-resolution forecasts for specific communities. Applied Ocean Sciences is proud to announce that we are merging with Entanglement Inc. to deliver next-generation quantum-enabled AI solutions for environmental and oceanographic challenges. Our core technologies deliver trusted, high-performance results with superior accuracy while operating with an order of magnitude less power. Our technology includes QUBO, the quadratic unconstrained binary optimization, quantum and simulated annealing, taboo search, and metaheuristics, which you'll hear lots more about tomorrow from Chris Verlinden, one of my colleagues. A few quantum challenges we want to address are stochastic modeling and simulations, where there's large ensemble realizations and parallel worlds, estimating of local probability distribution functions. We also would like to look into modeling chaotic systems, which are naturally highly nonlinear, which is a perfect application for these technologies. Faster on that one. All right. Also, weather forecasting and geophysical modeling, where you can improve the accuracy and ranges of weather forecasts by enabling more complex solutions and combining weather models and Earth ecosystem observations through such methods as QUBO, matrix inversion algorithms, and inverse modeling. We'd also like to look into quantum sensing in observing networks and simulations, where we combine quantum sensing and physical and forecast models to enable observing more details and create digital twins with augmented reality. The Quantum Almanac is the application of these next-generation computing technologies to environmental forecasting tools, where we leverage quantum computing and quantum-inspired algorithms utilizing fundamentally probabilistic Bayesian and ensemble-based methods. Examples of the, we're just gonna skip that one. All right, so we might all be familiar with the Old Farmer's Almanac, which you can think of as the original way of letting data lead the story. And we're taking this to the next generation with our Quantum Almanac, where we'll be using such things as our orthogonal matching pursuit and enable more accurate downscaling through quantum-enabled data assimilation and Bayesian ensemble probabilistic forecasts. What makes, there you go. These targeted forecast specifics, it's really hard to predict right now if it'll be raining on Tuesday at 1 p.m. and we're acting upon these false precision that we're getting in our current forecasts. And so using probabilistic methods, we're hoping to create applications in such areas as wildfire vulnerability forecasting, visibility predictions for maritime traffic, water availability and crop yield prediction for farmers, and solar panel performance for energy production and consumption. With these forecasts, we also need to deliver this information. This is one example where we use for water availability, where we're able to apply these methods and give forecasts in lead times greater than what people are currently experiencing, so they can act on them sooner. One case study I'd like to go through with our Quantum Almanac is the Pacific Palisades fire from January 2025. Tens of thousands of people, with up to 200,000 people, were under evacuation orders at one point, and advanced information would be helpful. So we take into account a variety of meteorological and climatological fields. In this case, we can think about temperature and wind, humidity, precipitation, but you could also think about fuel availability and topography. So if we look at a traditional global model on the left-hand side, the intensity as you go to yellow is a higher fire risk. And we can look, the circled area is the Pacific Palisades area. And so we can see it is fairly low resolution. And if we look at a 2-week forecast from our methods applied on the right-hand side, you can see that it's increased nuance and more actionable data that people could act upon sooner and respond to. If we look at this is just a bit of a comparison. On the y-axis is the forecast range versus the resolution on the x-axis. We can compare that 2-week global model versus our model on the top right, and then a 1-day model below. So in summary here, the Quantum Almanac is just one tiny example of what we can do with our next generation computing technology enabled by quantum AI for environmental forecasting tools, where it's rooted in ensemble-based predictions targeting long-term environmental forecasts. If you'd like to find out more about our capabilities, you can follow the QR code or talk to either my colleagues that are here, and Dr. Chris Verlinden will give another talk on this tomorrow in more detail. Thank you.
And to follow up on that one, we have delivering accuracy in the face of wildfire challenges, Dr. Huairen Ye.
Thank you. First of all, I would like to thank all of you for sticking around, even though the IT system doesn't seem to be. My name is Huairen, and I lead a data science team at Guidewire, which is a leading software provider for the insurance industry. My team specializes in building AI and machine learning solutions to help our clients to make better risk assessment and management solutions strategies. So wildfire, yeah, we've all seen the news. Wildfire are becoming more frequent and severe, which pose a great threat for the insurance industry. Carriers are having a really hard time staying profitable in high-risk market. For example, California. When that happens, they have no option but to forfeit the entire territory, which left homeowners being self-insured, which is a fancy way to say being uninsured. They are having challenges getting insurance for their properties, so when they lose their homes, they are totally exposed. So here's where we come in. We would like to empower our clients with the best possible risk assessment tool out there. We would like to really drill down to location-specific risk assessment. Now, when we're talking about wildfire, there are two things. First is the natural hazard risk component. And the second one is the conditional impact component. What does that mean? Okay, first we would like to know how likely is a location going to experience a wildfire at the first place. And then when that happens, we would like to understand, given the wildfire, how likely is the fire going to reach the property and cause a damage. So my team trained the models on millions of records using machine learning techniques. At the end of the day, we will be able to provide predictive risk scores for these two separate dimensions, as well as a final composite score that combine both. Here's an underwriting example in case you ever wonder why your insurance quote got declined, if that ever happened. So if a property is scoring high on both dimensions, meaning that it's very likely to experience a wildfire, and when that happens, it's very likely to get damaged. Then for those properties, we would like to refer them to specialists or avoid taking in this risk in our book of business at the first place. If a property is scoring moderate to high risk on either dimension, then underwriting due diligence is warranted. We would like to order inspections or check area imageries and then make an educated decision. Then if a property is scoring low on both dimensions, meaning that those are very safe risks to take. So we can do straight through underwriting, simple and easy. Okay, yeah, that's just a minor pretty color here for a bit. We are geographers and we love maps. So in almost every single presentation I did, I make sure there's a map for us to admire. So here we map out our newest wildfire product in LA County. The zip codes up here are under-marketed zip codes identified by CDI. So if a carrier is using an outdated risk assessment tool, for example, if the risk assessment is based on territory or zip code, what happens is they're going to see high risk across the board. They're not going to be able to distinguish relatively lower risk in these high-risk areas. As a result, as I mentioned earlier, they just have to forfeit all of zip codes. They can't write in those zip codes. Sure, we have California FAIR Plan, and the limit is $2 million. For all of you who are living in New York, you can appreciate that because properties in this region, they cost a lot more than $2 million. So according to our wildfire model, risk level still varies from location to location. What this means is that carriers can still select lower risk properties in this region and take them into their portfolio. Or for moderate to high risk properties, what they really need to do is to do actual risk-based pricing. So what we empower carrier to do is to assess risk at location level because all of our model components are calculated at location level. So our risk assessment is at location level. Now, when we're talking about wildfire, we also have to talk about mitigation. For those moderate to high-risk properties, homeowners can also work, carriers can also work with homeowners to develop mitigation strategies. For example, defensible space, making sure your vents are closed. There's fairly simple and easy ways to mitigate risk of your property. And then carriers can potentially assign discounts on the premiums they charge. But before we take any of those actions, we need to understand the risk level of the property. And that's why we developed this model to help our carriers move back to those high-risk market and help homeowners to have insurance to protect their homes and communities. That concludes my talk. Thank you very much. And if you have any questions, feel free to reach out afterwards.